Glass is one of the most important materials ever created by humans, shaping everything from architecture and transportation to food storage, medicine, and technology. Yet few people ever consider how ordinary sand is transformed into perfectly clear, rigid, and durable glass. What looks simple and transparent is actually the result of extreme heat, precise chemistry, continuous molten flow, and some of the most intense industrial conditions on Earth. From ancient discoveries along desert trade routes to towering modern furnaces running nonstop for decades, glassmaking is a story of fire, chemistry, and engineering at massive scale. And today on the How Factory, we're going inside modern glass plants to see exactly how glass is made. From raw sand to perfectly clear products used around the world. Humans discovered glass thousands of years ago, likely by accident. Early civilizations found that sand mixed with certain minerals could melt and harden into a shiny, translucent material when exposed to extreme heat. Ancient Mesopotamians and Egyptians began shaping glass into beads and vessels, while Roman innovations later introduced glassblowing, allowing for larger and thinner objects. For centuries, glass remained rare and expensive, made in small batches using wood-fired furnaces. Everything changed with the Industrial Revolution, when coal-fired furnaces, mechanization, and chemistry transformed glass into a mass-produced material essential to modern life. Modern glass production begins with raw materials arriving at the factory in enormous quantities. The primary ingredient is silica sand, chosen for its high purity and low iron content. Iron impurities give glass a green or brown tint, so sand used for clear glass must be carefully selected. Alongside sand, soda ash is added to lower the melting temperature, and limestone stabilizes the final glass, making it durable and water-resistant. These three materials form the foundation of most common glass. Factories also use cullet, recycled glass, which plays a critical role in modern production. Cullet melts at lower temperatures than raw materials, reducing energy consumption and improving melt consistency. Recycling glass is not just environmentally beneficial, it is essential for efficient production. Incoming materials are weighed precisely and stored in massive silos before being fed into batching systems. Batching is where chemistry meets automation. Computer-controlled systems measure exact proportions of sand, soda ash, limestone, and cullet. Even slight deviations can affect clarity, strength, or melting behavior. The dry ingredients are mixed thoroughly to ensure uniformity before entering the furnace. At this stage, the mixture looks like pale gravel, nothing like the smooth glass it will soon become. The heart of glassmaking is the furnace. Glass furnaces are among the most extreme industrial environments on Earth, operating continuously at temperatures exceeding 1,600 degrees Celsius. Once started, a furnace may run non-stop for 10 to 20 years without cooling down. Shutting it off would destroy the internal structure. The batch material is fed into the furnace steadily, where it begins to melt almost immediately. Inside the furnace, the transformation is violent and chaotic. Solid materials liquefy, gases are released, and chemical reactions occur. Soda ash decomposes, releasing carbon dioxide. Limestone stabilizes the silica network. The mixture becomes a glowing, molten liquid resembling lava. This molten glass must be perfectly homogeneous. Any unmelted particles or trapped gas bubbles would weaken the final product. As molten glass moves through the furnace, it undergoes refining. Bubbles rise to the surface and escape, while convection currents help mix the melt. The glass flows slowly, guided by gravity and furnace design, toward the forming area. This journey can take many hours, allowing time for impurities to dissolve and gases to escape. From the furnace, molten glass enters the forming process, which depends on the product being made. For flat glass used in windows and architectural panels, the float glass process is used. The molten glass flows onto a bath of molten tin. Because glass is less dense than tin, it floats, spreading out into a perfectly flat sheet. Gravity and surface tension naturally smooth both sides, creating glass with exceptional flatness and clarity. As the glass floats across the tin bath, thickness is controlled by rollers and flow speed. The ribbon of glass gradually cools as it moves forward. Once it solidifies enough to handle, it leaves the tin bath and enters the annealing layer, a long temperature-controlled tunnel that slowly cools the glass. Annealing is critical. If glass cools too quickly, internal stresses form that can cause cracking or spontaneous breakage later. For container glass, such as bottles and jars, molten glass is cut into precise gobs using mechanical shears. Each glowing gob drops into a mold where it is shaped using compressed air or mechanical plungers. The glass expands and conforms to the mold, forming the container's shape in seconds. Molds are cooled carefully to prevent sticking and ensure surface quality. Glass forming happens at astonishing speed. Modern bottle machines can produce hundreds of containers per minute, each formed, cooled, and transferred automatically. Despite the speed, precision is extreme. Wall thickness, neck dimensions, and weight must all meet strict tolerances. Once formed, glass products are still extremely hot and fragile. They must undergo annealing. Containers and flat glass pass through annealing layers where temperature is reduced gradually over long distances. This controlled cooling relieves internal stresses and gives glass its strength. Annealing ovens are carefully tuned. Even small temperature gradients can compromise product integrity. After annealing, glass enters inspection. Modern glass plants use automated inspection systems equipped with high-speed cameras, lasers, and infrared sensors. These systems detect cracks, bubbles, inclusions, thickness variations, and surface defects invisible to the human eye. Defective glass is rejected instantly and sent back for recycling as cullet. For flat glass, additional processing may follow. Glass can be cut, tempered, laminated, coated, or shaped, depending on its final application. Tempering involves reheating glass and rapidly cooling it with air jets, creating compressive stresses that dramatically increase strength. Laminated glass sandwiches plastic layers between glass sheets for safety and sound insulation. For containers, finishing operations include applying coatings that improve scratch resistance and strength. Some bottles receive decorative treatments or labeling directly on the production line. Others are packaged immediately for shipment to food and beverage producers. Quality control remains constant throughout the process. Samples are tested for optical clarity, strength, chemical resistance, and thermal performance. Glass must withstand temperature changes, pressure, and impact depending on its use. A glass bottle, for example, must survive filling lines, transport, and consumer handling without failure. Behind the scenes, energy management is a major focus. Glass furnaces consume enormous amounts of energy. Modern plants use regenerative burners that capture waste heat from exhaust gases and reuse it to preheat incoming air, dramatically improving efficiency. Electric boosting may also be used to stabilize furnace temperature and reduce emissions. Environmental control is equally important. Glass plants operate filtration systems to capture dust and emissions. Recycling rates are constantly improved to reduce raw material consumption. Because glass can be recycled endlessly without loss of quality, many factories aim for high cullet percentages in their batches. What makes glass manufacturing remarkable is the balance between chaos and control. Inside the furnace, materials melt and flow like liquid fire, yet the final product must emerge flawless, uniform, and predictable. The process relies on physics, chemistry, and gravity working together under extreme conditions. From ancient glassmakers shaping molten blobs by hand, to modern factories producing kilometers of flawless glass sheets every day, the core principle remains unchanged. Heat sand until it becomes something entirely new. What has changed is scale, precision, and consistency. From raw silica sand and recycled glass to roaring furnaces, floating tin baths, precision molds, and endless inspection systems, the journey of glass is one of the most dramatic transformations in manufacturing. Every window, bottle, screen, and lens begins as grains of sand subjected to controlled fire. And that is exactly how glass is mixed, melted, refined, shaped, cooled, inspected, and shipped, transforming ordinary sand into perfectly clear products that shape the modern world. Thanks for watching The How Factory, where we reveal how the world really works. Don't forget to like, subscribe, and join us again for more deep dives into the machines, materials, and factories behind everyday materials.